Just like we call our friends with their names, the devices on computer networks identify each other's using an IP address. That's the first thing any device need when joining a network. Here, the iPhone has the IP 192.168.0.1. Meanwhile, the PC has the IP 192.168.0.2. This address can be assigned either manually or using DHCP. The device you are streaming with right now has at least one IP address. This IP is assigned to the NIC that comes built in with the device. And just like we can have many names and nicknames, one device can also have multiple IP addresses if there have multiple NICs attached to it. This laptop here has two IP, one for the Wi-Fi connection and one for the Ethernet connection. So how many NIC do you think your PC has right now? You can find out about this from the device manager. We can keep on adding more NIC to any device as long as it has enough interfaces to support the new adapters. When we have more NIC, our device can join more networks concurrently as backup networks or for improved network speed. Here we added a 5G dongle to the laptop so that we can connect to Maxi's 5G network anywhere we go. Now, let's talk about source and destination IP. In any data communication, normally there is one sender that is sending data to a receiver. This is called a unicast communication. The IP address of the sender is the source IP, and the IP address of the receiver is the destination IP. Looking closely at the packet header, we can see the source IP is 192.168.1.1, which is the IP of the iPhone. And the destination IP is 192.168.1.2, which is the IP of the PC. There are several networking rules in IP addressing as outlined in the layer 3 of the OSI layer. These set of rules are important so that all devices can communicate with each other using one universal language. Here, we will go through the 5 important IP subnet rules. The first rule says that every IP address assigned to hosts in a local area network must be unique. This means that the same IP address cannot be assigned to two different hosts in the same LAN at the same time. Looking at the network on the left, both PC has different IP addresses. This addressing scheme obeys the IP rule number 1. Meanwhile, look at the network on the right. Both devices are using the same IP address. This subnet will later runs into connectivity issues due to IP conflicts. Why is Rule 1 important? Let's take a look on a simple network with 3 PCs. In this network, all 3 PCs are assigned with unique IP address each. Imagine that PC3 is sending a packet to PC1. In this case, we know that the source IP would be PC3's IP address and the destination IP would be PC1's IP address. Based on this destination IP, the network switch knows to forward the packet to PC1 instead of PC2. That's how the packets can travel to the right destination. Actually, a switch refers to MAC address instead of an IP address. We will talk more about these later. In the second network with the same topology, notice that both PC1 and PC2 is using the same IP address. When PC3 sends a packet to PC1, the network devices will again forward the packets based on the destination IP. Here, the network device cannot figure out which physical ports to forward. Should it send the packet to PC2? Or should it send the packet to PC1? This is because right now both hosts are having the same destination IP. Now let's move on to the next IP rules. The second IP rules state that every networks need a network address so that they can be reachable from other networks. The addresses you see here, these are network address. So firstly, we will understand why is network address important for data communication. Then, we will learn how to find out what's the network address for private networks. This Google map currently shows several small towns in Malaysia. In real addressing, areas that are geographically divided have their own area code. Houses in the same area share the same area code. So, you bought a new Bose soundbar. To ship this parcel, the FedEx guy locate us based on the area code of our house first before looking at our house number. Now let's look at an example. Here, Avocado wants to go IKEA for some free coffee by train. The spots circled in red, those are the train stations. You see, for Avocado to reach IKEA, he has to stop at the train station closest to IKEA. From there, he can take a grab car to IKEA instead of walking. Notice that he cannot take the train from his origin to IKEA directly, because there's no station attached directly to IKEA. Here, the train station acts as the proxy to all other destinations in the coverage of the green-colored box. If Avocado wants to go back to his condo which is in the same area as IKEA, he would take the same path and go to the same train station. Now, what if Avocado want to go to the bank in the blue-colored zone? For that, he would have to stop at the train station attached to the blue-color zone. This addressing scheme is highly similar to addressing in computer networks. Here's are some networks built based on the maps we saw earlier. Looking at the network in the green-colored box, we have PC1 and PC2 that are connected to a switch that connects to a router. Here, the router acts like the train station for this network. All packets intended for the hosts in this network, regardless of going to PC1 or PC2, they will be sent to this router. Imagine someone on the internet sends a packet to PC1. The outsider used the IP 10.10.10.1 as seen in the source IP of the packet. The packet is going to PC1 with the IP 192.168.1.1. For end-to-end delivery of this packet, the remote router must first find out the destination network address that PC1 is located in, which is 192.168.1.0. All packets going to this network must be sent to the edge router of the network, which is having the IP 192.168.1.254. So in general, packets are forwarded to other networks across multiple routers based on the destination network address. For example, when someone sends a packet from the network in blue to network in yellow. This packet is being forwarded to the next hop based on the destination network found in the packet header. This complex process is handled by the routing protocols. Now that we know what is the use of network address, let's take a closer look at the network address structure and how we can find the network address in computer networks. So, this is an IPv4 address assigned to a host. In every IP address, it can be separated into two sections, which is, the network bits and the host bits. Now, this is a network address. The /24 in the address is the subnet mask for this network. A subnet mask is used to determine the boundaries of a network. This number can changes depending on how the addressing scheme is designed. For example, the subnet mask for a network A can be /24, and the subnet mask for network B can be /28. Remember that in each IP there is a network portion and a host portion? The subnet mask, visualized in this line here, will determine the boundary of the net bits and the host bits. The boundary here can tell us how many network bits and how many host bits are there in an address. Look carefully at how the changes in subnet mask happened when it is slide to the left. When we move the slider to the left, this means we are reducing the number of network bits, and at the same time, the number of host bits available is increased. Notice that now the mask value has changed from /16 to /8. Similarly, when we slide the subnet mask line to the right, We are increasing the number of net bits, and at the same time, reducing the number of hosts bits. Again, notice how the subnet mask values changes from /8 to /24. We will talk more about this value in a while. So the idea here is that we can play around with the subnet mask value in deciding what kind of addressing scheme to use. For example, if we need to build many different networks, where each network will have a unique network address, then we should slide the mask to the right. This is because having more network bits allows us to create more networks. Meanwhile, if we want to add many hosts in a single network which requires more host IPs, then we should slide the mask to the left so that we can have more hosts bits available. This translates to more usable IP address in the pool that can be assigned to end devices. Now let's take a look at the value of the subnet mask. For simplicity, we will start with the subnet mask in classful addressing. In the classful addressing, IP addresses can be divided into Class A, Class B, Class C, Class D and Class E. For now, we will only focus on Class A, Class B, and Class C. Remember that each IP address is 32 bits long. There are 4 octets in an IP address, where each octet is 8 bits long. In Class A, only the first octet is used as the network bits. This means all Class A IP address has a /8 mask. Meanwhile in Class B, the first 2 octets are used for network bits. This means that all IP address in Class B will have a /16 mask. Lastly, the Class C address use 3 octets for network bits. This means that all Class C address has a /24 mask. So, here's a table to summarize the subnet mask for classful addressing. In fact, there are many ways we can represent the subnet mask. In the slash notation we saw earlier, the number of network bits is written after a slash. Normally, we write mask in this notation as is seen in the lecture videos because it is quick and simple. Next, we have the decimal notation. This notation is useful for real-world configurations like setting up a Cisco router. Machine only understand this notation as input, but not the others ways of writing. Lastly, we have the binary notation. We only convert mask from decimal to binary when some calculation works are required. For example, to find the network mask we need to perform the n operation with the addresses in the binary format. First, let's take a look at the /8 mask. /8 means the first 8 bits of the address is used as the network bits. Translating this to binary notation, this means that all the bits in the first octet is set to 1. Further translating this binary to decimal notation, we have the value 255 in the first octet. For the /16 mask, we have the first 16 bits used as the network bits. Equivalently, this means the first 2 octets are all set to 1 in binary notation, and we get 255.255.0.0 when translating this to the decimal notation. Lastly, for the /24 mask. Here we set the first 24 bits as network bits. In binary notation, this means the first 3 octets are all set to 1. Meanwhile, we get 255.255.255.0 in the decimal notation. For better clarity, we will now demonstrate how we get these subnet mask values. First, let's look at the /8 mask in the binary notation. Again, there are 4 octets in an IPv4 address. Each octet is 8 bits long. In /8 mask, the first 8 bits are for the network bits. And the last 24 bits are for the host bits. Here, the first 8 bits is set to 1, while the remaining 24 bits are all set to 0. Remember that machines only understand the decimal notation. We can translate these binary values into decimal quickly using an IP calculator. Here, we get 255.0.0.0 after the conversion. Next, we look at the /16 mask in binary. In /16 mask, the first 16 bits are for the network bits. And the remaining 16 bits are for the host bits. Here, the first 16 bits are set to 1. While the remaining 16 bits are all set to 0. Using an IP calculator, we can translate this address into 255.255.0.0 in the decimal notation. Lastly, we look at the /24 mask in binary. In /24 mask, the first 24 bits are for the network bits, and the remaining 8 bits are for the host bits. Here, the first 24 bits are set to 1, while the remaining 8 bits are all set to 0. Using an IP calculator, we can translate this address into 255.255.255.0 in the decimal notation. Now that we've understand fixed subnet mask, next, we will look into how we can use these subnet mask to calculate the network address of computer networks. Remember that packets travel to the right destination based on the destination network address. To be clear, end hosts do not need to know the destination address. In fact, the end host only needs to know the IP address of the destination hosts. The network address is automatically calculated and figured out by routers on the internet. Now, let's take a look at an example of network address calculation. There are two things we need to calculate the net address for any networks. The first thing is an IP address within the network. This can be an IP address assigned to any hosts inside the LAN. The second thing is the subnet mask, which we've just learned earlier. Before we start calculating the net address, let's quickly recap on the n operation of binary numbers. Given two input bits of binary numbers, a 0n with a 0 gives us an output 0. A 0n with a 1 gives output 0. 1n with 0 gives output 0. 1n with 1 gives output 1. So, in the n operation, only two 1s will give us an output of 1. Now we are ready to calculate the network address. In this example, we are given an host IP 192.168.1.1. And the subnet mask for the network is 255.255.255.0. We can tell that this is a /24 address. So, the first thing we do is to write these addresses down in two separate lines. Then, we need to convert this address from decimal to binary notation for the n operation later. You can get binary values quickly using a scientific calculator, or using rapidtables.com. Remember that we need to convert for both the host IP and also the subnet mask. Another quick tips. The value 255, in decimal, converts to 8 ones in binary, so you can skip the calculator for this one. Next, we perform the n operation using the host IP and the subnet mask. Starting from the leftmost bit, a 1n with a 1 gives an output 1. We write this output in the first bit of the network address. Then we continue with the next bit to the right. At the third bits, a 1n with a 0 gives 0. So we write this 0 bit in the third bit of the network address. Going from left to right this way, we will get the full, ended, address. This is the network address in binary notation. For clarity, we will convert this address back to decimal notation. Again, pressing the calculator, we will get 192.168.1.0. which is the network address of this network. So, there you go. That's how we can calculate the net address of any networks. Okay. Now let's summarize what we've learned. Network address is just like the area code in our map. Network packets are transmitted over the internet based on this address. We can easily get the network address of any network, if we know the subnet mask of this network, and also one of the host IP inside this network. In this example, we derived the network address by performing the n operation of these two addresses. So, the network address of this LAN is 192.168.1.0. This means that packets from the outside that are going to any hosts within this LAN should be sent to this address. Okay. In this video, we've talked about the first two IP subnet rules. To recap, remember that the IP addresses used by the host in a single LAN has to be unique. This is to prevent IP conflict that can result in connectivity issues. Then, recall that for every networks to be reachable, they need to have a network address. In the next video, we will continue with the third and fourth IP subnets rules with more intuitive examples. See you again.